Now, I have huge pleasure and honour in introducing to you Terry Mosely. Terry, come to the stage.
Sorry?
Come hither.
Right.
Terry is a past president of the Irish Astronomical Association based in Belfast, and he's widely regarded as Ireland's foremost amateur astronomer. And it's a great privilege for Cork Astronomy Club to be able to welcome him tonight in order to open our season of public lectures. So I'll say no more. I shall put you in Terry's hands. Terry, the floor is yours.
Thank you very much. I didn't care to say that. Right, it is a great honour and privilege to be back. I have lost count of the number of lectures I've given to the club. I was trying to work it out from just sort of dates and so on. It's either the 7th or the 8th, and why you're not fed up with me, I do not know. The first time I think was probably about 1995, and obviously it was only a wee young boy in shorts then. Those that know me will know that you can laugh at a joke like that. But seriously, it is a great honour to be back and see a lot of familiar faces and some new ones as well. Now, can you sort of lead me on to the next thing, because I don't want to upset anything on this here, since I'm not used to your particular setup. I've given talks on every topic was different. This one is one I've come up with relatively recently, and you need to go back a wee bit. Right, okay. So, if anybody's here to hear a lecture about amphibians and felines, I'm sorry, you're going to be disappointed. But I always think it's a good idea to have a sort of an interesting, thought-provoking title for your talk. So we'll find out about newts, cats, spets and ogs as we go along. So is it just the down arrow? Okay. So I'm relatively old-fashioned. A lot of stuff I'm going to be saying here is simply what's on the screen, but I think that's a good idea because it enables you, if you want to make some notes as you go along, or if you want to take a snap of the screen, feel free to do so. So basically, as it says there, in terms of the inventions of astronomical equipment, you could give 10 lectures and still keep it at a popular level, and you could give 100 lectures if you want to go into the technicalities. But I'm not going to talk about every telescope, and not just about the biggest telescopes, and not just about the first of a particular time, but a bit of a mixture of all of those. And it's really through the telescopes, and I'll be saying a little bit about what we have learned from them as we go along. So here's the explanation bit. A newt, obviously, short for a Newtonian telescope. Cat is short for catadioptric, which is a type of telescope that uses a combination of mirrors and lenses, like Schmidt-Cassegrain, for example. Spec is short for speculum, and we're now starting to get into the sort of the history of astronomy a bit. The old name for a telescope mirror, because it was made out of speculum metal, like the big one at Birr, which I think a lot of you have probably seen. So astronomers back in those days would have written about their telescope as a speculum, because it used a speculum mirror rather than an object glass, which is the next one we come to. The old term for the front lens of a refractor. And when I started observing, and I was using mainly the 10-inch refractor at Armagh Observatory, and I was making a note of what I was using, I didn't write out 10-inch refractor, I just wrote out 10-inch OG, short for object glass. So that's what an OG is. And there are various others that we come to later in terms of other types of telescope. Those are the main ones. And then, of course, there's all the other things in the electromagnetic spectrum and others that come into play. Now, first telescope. Most people think Galileo, but it wasn't. There's a Dutch optical guy, spectacle maker, Hans Lippershey, or Lippershey, there are two different spellings, and he applied to the States General of the Netherlands on 2nd of October 1608 for a patent, which was basically a telescope. an instrument for seeing things far away as if they were nearby. Very simple refractor. You can read what's there in terms of the definition of it. I'll not go into all the detail. The Dutch perspective glass was the name that was used at the time. Now, the interesting thing is that he possibly and probably was not the first, because he wasn't given the patent, because other people had made them as well. But this is the first official record of a telescope that he applied to the patent office for the design of the telescope. But it was that round about then that the very first telescopes were made. He may have been the first, but when he applied for the patent, he wasn't the only one that had made telescopes. So he didn't get the patent, but we have that record, and that is the first official record of a telescope. Now, again, a lot of people think, well, Galileo was the first one to use it for astronomy, but no, he wasn't. Thomas Harriot, 1560, born in Oxford and died in London 60 odd years later, and he was the first to make a drawing of the moon through a telescope with a magnification of 6 on the 5th of August, about 4 months before Galileo's first observations. Now, it's not a great map, but it does show the features. It shows some of the things that are not visible to the naked eye, and it therefore does indicate that he used a telescope to make that observation. So that is the first recorded astronomical observation with a telescope. There may have been others, but if so, they're lost. We don't know about them. However, Galileo was the first to do proper astronomical observations rather than just sort of drawing what he might see. There's all the details about him. There have been numerous books and even films and TV programs about him, so I'm not going to all the details there, but he's best known, for example, for the things that revolutionized our conception of the universe, which up to then a lot of people had thought was Earth-centered. The Earth was the center of everything. For example, when he discovered the main moons of Jupiter, the Galilean moons, it was discovered that they revolved around Jupiter, not around the Earth. Therefore, the Earth was not the only center of revolution in the universe, and that was a big sort of paradigm shift for people. He discovered the rings of Saturn, although his telescope was not powerful enough to show exactly what they were like, but you could see that it wasn't a round disk like Mars or Jupiter. So he recorded that, but he couldn't actually resolve them into the rings. He drew the phases of Venus, and Venus could only exhibit phases if it was revolving around the sun and not around the Earth. So that also sort of got rid of the Earth-centered view of the universe. There are other things as well. Those are the two main things. I'm going to come back to that in a moment. When he looked at the Milky Way, it wasn't just sort of a misty band of light. It was, as he described it, composed of innumerable stars, and he recorded sunspots as well, and that showed that the sun was rotating. And another thing, the drawing of the lunar craters showed that the moon was not a perfect sphere. It had imperfections. It had sort of blemishes, if you like, on it. And why that was so important was that went against the teaching, which was accepted by the Catholic Church at the time, that the Earth was the centre of the universe and everything went around it. Those three bits of evidence there, the main moons of Jupiter were revolving around Jupiter, the phases of Venus showed that it was revolving around the sun, and the fact that the heavens were not perfect because the moon had these blemishes or craters on it. That basically shut down the Earth-centred view of the universe. The Church didn't like that. He was forced to curse, abjure, and forswear his theory that the sun was the centre, at least, of the solar system, if not the universe. Bruno was burnt at the stake because he wouldn't recant and so on. There's far too much to go into that, but basically Galileo is the first one to challenge the Church on that. And that was the start, if you like, of the paradigm shift, if you like, a sort of a conflict between the scientific view of the universe and what the Church had been teaching over all the years. Still goes on to a certain extent, but I'm not going to go into that. So Galileo basically began modern observational astronomy, and as I've been saying there, sorry, I didn't realise that was coming up. So that's more or less what I've been saying. So I'm going to skip just to this last bit a little bit here. The telescope was only about just over half an inch diameter, tiny, focal length of almost a metre, and a magnification of just 21, which is a bit more than a good moderately high power binoculars. A field of view of only 15 minutes, that's about half the diameter of the moon. But what he did with it was revolutionary, and that basic design of using optical elements to produce a magnified image and to gather more light has led on to the most powerful telescopes in the world that we have at the moment, the Very Large Telescope and the Hubble and the James Webb Space Telescope. So, another great name in the history of astronomy, Kepler. Anybody that studies a bit of astronomy will know about the Kepler's laws of planetary motion, and that's a topic for another talk. But he also designed a type of telescope, and not a lot of people actually know this. The Keplerian telescope uses convex lenses for both the object glass and the eyepiece. That was better than Galileo's design, and that led to another astronomer, Christian Huygens, a Dutchman, developed very, very long focus telescopes. And the reason they were very long focus was for two reasons. First of all, a single lens, a lens made out of a single piece of glass, has what we call chromatic aberration. It doesn't bring all the colours of light to focus at the same point. Red and blue will come to foci at different points. One of the ways, not the only way, but one of the ways to minimise that is to make the focal length as long as possible. My very first telescope was basically a 2-inch lens, but with a focal length that long, because I couldn't afford a proper, what we call an achromatic lens. I'll mention that later. Also, the longer the focal length, the higher the magnification. And it led to extremes like this here, which is a total monstrosity. How anybody ever managed to see anything through it, I don't know. It'll be all right if the sky was stationary, but the Earth has this unfortunate habit of rotating on its axis, which means that everything moves across the sky. But that was an attempt to minimise chromatic aberration, to give an image that wasn't all sort of mixed up colours with colour fringes, and also to get a very high magnification. But as you can imagine, totally impractical, and they didn't really catch on. I've often wondered if it would be possible to try and reproduce that and see if it was actually possible to actually see anything through it. You're trying to point it to something which is continually moving. Anyway, another guy comes into the equation next, and at this stage it's largely the development of new types of telescopes, new designs. James Gregory, and the Gregorian design was quite popular for a while, then it faded out, and now, believe it or not, it's making a comeback, at least in some cases. So this is also a reflector telescope, and the reason why this is easier to make than the other is that both of the optical surfaces can be tested by what's called a Foucault test. I'm not going into the details of that, but basically you're moving an object through the beam of light at the focal point, and how the mirror surface darkens as you move an intervening object enables you to test the accuracy of the surface. So you want a parabola for the primary mirror and an ellipse for the secondary mirror. It was a slightly longer design. We'll come to the Cassegrain and the other design in a moment. The secondary mirror is outside the focal point. There's the focal point there. That means you have a slightly longer tube. And for those of you that are relatively new to astronomy, there are some people here maybe for the first time, this sort of design is not with your sort of capped and pugwash telescope with the lens up at the front. You have nothing at the front except a secondary mirror there. The light goes down the tube and it hits the surface of this curved primary mirror, and that reflects the light back up to a secondary mirror in the middle of the tube, and then it not only reflects it back down the tube, but it changes the focal length because the beam is a narrower, a more pointy beam. So that has the effect of actually, in theory, magnifying the focal length, increasing the focal length of the telescope. The other design, which we're going to come to in a moment, is shorter because the secondary mirror is inside the focal point. So the Gregorian was fine, did the job well, but it wasn't as compact. So, as I said, it never really caught on because other designs superseded it, but it's now coming back in. And for some of the major telescopes in the world, the Twin Magellan telescopes, 2 mirrors, 6.5 metre diameter. The large binocular telescopes, 8.4 metre. The Daniel K. Inouye Solar Telescope, 4 metre. That's the largest solar telescope in the world. And then one that's being planned at the moment, may or may not be built, the Giant Magellan Telescope, 7 individual mirrors, 8.4 metre diameter, and those individual mirrors are all of this Gregorian design. So it sort of went into abeyance for a while, but it is now making a comeback. It's not the only design of the new telescope, is certainly one of them. Now, Cassegrain, this is the one that most of you who have telescopes may well be familiar with, in the Schmidt-Cassegrain design. So we'll do Cassegrain itself first. This is, as I was saying, a design where again you have the light hitting the curved primary mirror. It goes up and strikes a secondary mirror before it reaches the focal point, which would be up about there. And that's hyperbolic. Now, a hyperbolic curve is quite hard to make and quite hard to test. So that's a design for experienced opticians, basically. But again, the net effect is you reflect the light back down through a hole in the primary mirror, and you have your focal point, so your camera or your eyepiece is there. And lots of you, if you've been to a star party, you have almost certainly seen the telescope of that design. Now, we'll talk about the variation on that in a moment. And the largest one of those was this one here, a telescope that I've had the honour of seeing and actually climbing up on the mount there, because it's so substantial that even my mate doesn't do anything to it. That's the McDonald Observatory in Texas, and that's the largest one of that type at the moment. Just a Cassegrain, not a Schmidt-Cassegrain. And you'll see my little note there at the end. They have public viewing a few times a year, an 82-inch diameter telescope to look through that. But is it the largest that you can look through? Well, we'll come on to that later. They claim that it is, but they're not the only ones that make that claim. Now, everybody's favourite scientist, up to and maybe including Hawking, Sir Isaac Newton, did so much for astronomy and science generally, and again, subject for a lecture on its own. So, he invented the Newtonian reflecting telescope, and as I was saying with the other telescopes, they have no chromatic aberration. No reflector telescope has chromatic aberration because the light never passes through the glass. It falls on a reflecting surface on the front of the glass and is reflected away again. You may get chromatic aberration in the lenses and the eyepiece, but that's another story, and it cannot be avoided. So there's only one optical surface, the curved surface of the primary mirror, and that was a sort of a groundbreaker. It rapidly became the choice of telescope if you wanted a really big one. We haven't got rid of the refractors yet, but if anybody has a large, powerful, large aperture amateur telescope, it's probably a Newtonian reflector. So we'll talk about the knobs later. Okay, that then sort of superseded the Gregorian. It was simpler and cheaper to make than the Cassegrain. You did have a relatively long tube that you needed to mount and so on, but it wasn't insuperable. And for a long time, the Newtonians were sort of the best type of telescope for collecting light, more photons per dollar, per euro, per pound, or whatever. So there's the classic design. For example, the big telescope at Burr is basically a Newtonian reflector. The light goes down, hits the primary mirror, which is curved, reflected back up, and this time it's reflected out through the side of the tube, so the eyepiece is up near the top. And that is a flat surface, so that's very, very easy to make. Very simple design. The secondary mirror can be quite small, so it doesn't intercept as much light as the secondary mirror in a Gregorian or a Cassegrain, and relatively simple to use. Now, it doesn't give sort of the general public perception of a telescope where you're looking at the bottom end up through the telescope pointing up at the sky. You're actually looking sideways into the tube up at the top of it, but you soon get used to that. And it gives beautiful images, relatively easy to make accurately. You just have one mirror. It can be a relatively long focal length, f6, f7. In other words, the focal length is 6 times or 7 times the aperture of the mirror. That's relatively easy to make, and a flat secondary. And you can get exquisite images from a good Newtonian telescope. Now, this is where we come into the sort of the amateur revolution. A Californian Buddhist monk, John Dobson, who gave a talk at one of the Whirlpool star parties about 20 years ago, maybe, your actual John Dobson, invented this very simplified form of mounting. The telescope itself is just a straightforward Newtonian, but instead of putting it on a heavy, complicated, expensive equatorial mount, he invented this very simple mount. An azimuth turntable, just like basically a record player turntable, so it can turn right through 360 degrees, and a simple little friction bearing on the top of 2 side panels. And basically you mount the telescope so that that is at the point of balance of the telescope, or very, very nearly. And then it moves in the 2 main planes that you need to find anything in the sky. It'll move left to right, and it'll move up and down. The disadvantage is that things in the sky don't move like that, as you probably know. They tend to rise in the east, reach their highest point in the south, and set in the west. That's simplifying it a bit. So they're never moving just straight up or straight across, except for very short periods. So in order to follow something moving across the sky with that design, you need to move it simultaneously, both in what we call azimuth, horizontally. If you're looking south, you're moving it basically from left to right, and at the same time you have to move it up if it's rising, and you have to move it down if the object is setting. So it's fine for visual observing, not so good for photography, except now with your smartphone you can take pictures with very, very short exposures. But up until sort of like the last couple of years, if you wanted to do astrophotography, that was not what you chose. But it's possible to make quite a big, powerful telescope. Make them portable, because the tube does not have to be solid, or it can even be collapsible. It can be an open truss design. You can have, I know people in Ireland who have Dobsonian telescopes of 20-inch or 24-inch diameter, and that's a really, really powerful instrument. Beautiful instrument for looking for faint galaxies and nebulae and so on. But, as I say, they're not suitable for long exposure imaging. Transportable, I've seen them ones up to a metre, 40-inch diameter roughly, on a trailer. It didn't make any major discoveries, but it did bring practical astronomy with powerful telescopes to the masses, because you could make it relatively cheaply and relatively portable. You didn't need to put it in an observatory with a proper fixed mount, so you could put it in your shed or your garage or a spare room and take it out whenever you needed. So it revolutionised astronomy for the amateur. And as I was saying, the one at Mir is the world's biggest Newtonian, certainly the biggest in operation. You can see the length of the tube there, and there's the eyepiece where you're looking in at the side of the tube. And when I said it didn't make any major discoveries, that was the Dobsonian. The Newtonian certainly did a little bit of the details there. It was the first to resolve, built to resolve the nebulae, the messy objects. Where these things, these fuzzy patches in the sky, galaxies, collections of stars, were they gas or what? So the Whirlpool star party, which I mentioned, was named after Lord Ross's discovery of the spiral structure of M51, the Whirlpool galaxy. And it was the largest telescope in the world from 1845 to 1917. Very limited in its motion, simply because the thing is so huge, so it couldn't observe the whole sky. But if you wait long enough, any object in the sky would come into view in that telescope. You could follow something for about, depending on how high up it was, an hour or an hour and a half in between the two big giant walls there. And that gives you some idea of the size of it. There's yours truly. When it was restored, they thought, well, we can't have this thing operated just by the Earl's servants operating big hand winches and windlasses and so on. So it was given electric motors and hydraulics and computer control, and I was lucky enough to actually get using it and to see there be a nebula through it. It's a long, long story about what went wrong. It's not usable at the moment. If you buy me 10 pints, maybe, I might tell you the story. Health and safety got involved, and bureaucracy. But does anybody spot anything unusual in the photo?
You?
There's an extra hand there. Nick Howes, who some of you may know, a very well-known, popular astronomer from England, was over visiting, and I have sort of unofficial carte blanche to go into the telescope tube and inspect the mirror. I've done a few bits of maintenance on it. So as a wee treat, I took him down right into the bottom of the tube to show him the mirror. And somebody took that photograph. I don't even know who took the photo. I was given a bit of a talk afterwards. He was still in behind there, and he had his hand on, that's the mount for the secondary mirror, and I only spotted that afterwards. But anyway, it's not a ghost, it's a real human hand. Okay, the orbs, we haven't really mentioned them since Galileo. They had their heyday as well. They had the advantage that you could look through the bottom of the tube instead of up at the top of it, and they culminated in some very, very large telescopes, and there's a very strong local connection here. So I mentioned that an ordinary single lens telescope produces false colour. It doesn't bring the colours of light to focus all at the same point, and that's called chromatic aberration. Chroma is colour. But this guy, Chester Moore Hall, found that if you made a doublet lens with two different types of glass, where the chromatic aberration of one largely cancelled out the chromatic aberration of the other, crown glasses versus flint glass, you could quite largely get rid of the chromatic aberration. And that gave the refractor a new lease of life. The first ones were built in 1758 by John Donald, and thus it was possible to build bigger and bigger telescopes without making the tube too long and have quite reasonable images. Not perfect, there was still a certain amount of chromatic aberration, but it was acceptable. So the local connection is that Thomas and Howard Grubb of Dublin built the largest refractors in the world for a while. There was rivalry from America, but the largest one that they built was a 27-inch refractor at Vienna, and that was built in 1880, and at that time that was the largest refracting telescope in the world. It's good going for Dublin. The Clark brothers built even larger ones, and the largest one ever built is this one over here with a 40-inch diameter lens at Yerkes in Wisconsin, built in 1897. And this equatorial mount, called the German equatorial mount, what by then was the standard mount. I'm not going to go into the details of mounts except once more maybe, but that enabled you to follow an object across the sky by moving it in one plane only, because one of the axes pointed to the North Pole, or in the southern hemisphere the South Pole. So you only needed to rotate the telescope at right angles to that axis. Now, why didn't they build ever bigger ones? Two reasons. First of all, the light passes through the glass. So you have two bits of glass, crown glass and flint glass, and not only the surfaces of the glass, but the internals of the glass has to be perfect. No air bubbles, no little hairline imperfections. Otherwise the image would be destroyed. So to make glass banks much bigger than about 40-inch diameter, where there are no imperfections in the glass, became increasingly difficult. The other problem is that you obviously can only support the lens around the rim. And whenever the telescope is pointing up in the sky, these bits of glass are big and heavy. They tend to sag under their own weight. Glass is pretty rigid, but it's not totally rigid. So when you have a telescope like that with a huge lens pointing up in the sky, the lens sags very, very slightly under its own weight. And obviously the bigger the lens, the heavier it is, and the bigger it is, the greater the diameter across which you have the unsupported glass. So it became really impractical to build any refractors larger than that. That one was in use up until relatively recently. It's basically out of date now. Glass tends to gradually degrade even internally, and it's used just occasionally for public viewing. But to give you some idea of the scale, that's the staircase that you have to climb up to get up to the mounting here. Absolutely huge. I've never seen it, although I'd really love to. So that was really the end of the large refractors. You could still build one of that size if you wanted, but there'd be really very little point. For a start, you need a huge dome and a very heavy mount to mount something of that size. But there's still quite a lot of Grubb telescopes in use around the world. There's the 10-inch at Armagh, the 12-inch at Dunsink, and the two 12 inches here at the Crawford Observatory, I think, were built by Dublin for the Cartley Shell project, but I'm not going to go into that. So what took the record away from the telescope at Burr is the largest. That was the 100-inch reflector at Mount Wilson in California. It was designed as a Cassegrain, where the light would go from the main mirror up to a secondary mirror up there and back down through a hole in the centre of the main mirror, and that was, in theory, where you would do the observing. But the telescope was so big that they were actually able to use a lot of equipment right up there at what we call the prime focus. It was mainly used for photography, so literally you had a giant camera in there with glass photographic plates, probably 8-inch square or something like that, and the observer could go up and put the glass plates in the camera mounting there, give the exposure maybe half an hour, something or other, remove the plate and put in another one. So it was used mainly at the prime focus up there. Now, I said I wouldn't say too much about mounts because it's too complicated, but you will notice that that is a totally different sort of mount. It's what's called a yoke. There's the southern end of the polar axis there, because this thing, by the way, is big and heavy. That's all solid steel. And the north end of the other polar axis is mounted up on that big solid pillar there. And the telescope swings in between the two arms. There's two arms, one behind the other, one there and one other on the far side. But the problem is that the telescope cannot swing past the North Pole bearing there. So it cannot look at the North Pole of the sky. It can get within about 15 degrees of it. But nevertheless, that was a revolutionary telescope. The Burr 72-inch had its limitations. There was no drive. It was only speculum metal. By now they were making mirrors made of glass with an aluminium or silver reflecting coating on it, which was much better. And that was a very, very powerful telescope. It was more than twice as powerful as the 72-inch at Burr. So it was used by two very famous astronomers, Humason, you may have heard of, certainly Hubble. And they found, for example, that M31 was not just something in our galaxy, it was another twin separate galaxy, in fact quite bigger than ours, well outside our Milky Way galaxy. I haven't time to go into all the history of this or how it happened, but using that telescope they were able to prove that the universe was expanding, which was again quite a paradigm shock. And Fritz Zwicky found the first evidence for dark matter. Again, too complicated a subject to go into here, although I can try and answer questions on it afterwards if you want. Discovered that Cepheid variables, which had been used to measure the distance of the universe, actually came in two types, population 1 and population 2, which had different characteristics. And so the measurements that they had made of the size of the universe by measuring distances using Cepheid variables had to be recalibrated, and it was twice as big as they thought. And it is also claimed to be the largest telescope usable for visual observing. In other words, in theory, you can put an eyepiece back down in there. Yeah, it was a Cassegrain, so you could have the eyepiece there. Now, as far as I know, it's only used on very special occasions and only for VIPs. So you or I couldn't go along there on a clear night and say, can I have a look through the telescope? Please, pretty sir. But apparently it can be used for visual observing. So that probably holds the record. But the 82-inch McDonald one is used for public observing, not often, but certainly a couple of times a year. The biggest one I've ever looked through, apart from the 72-inch at Burr, and it was a very limited view. It's a 61-inch at Tucson in Arizona, and that's quite a mind-blowing experience, a modern high-quality telescope built by NASA for moon mapping. Right, some of you may know that I went on a trip to see the total solar eclipse in April there. I'm not going into that now, but basically we started off in San Diego, cruise ship down to intercept the line of totality off the coast of Mexico, did a bit of sightseeing in Mexico, and then back up to San Diego. And if you go to San Diego, you're not far from Mount Palomar, which during my days of growing up in astronomy was the mecca, if you like, of astronomy. By far the biggest and most powerful telescope in the world. The 100-inch at Mount Wilson was a doubling, if you like, of aperture compared with what is actually usable. This was the 200-inch. It is humongous. It really is. I knew the size, I knew the statistics. When you actually go there, it really is mind-blowing. You can look at the photos and it doesn't convey it. You have to go there. Anyway, that's yours truly with my little cap on. Inside, I took about 150 photos. That's just one of them to try and give you some idea. Before we look at all the figures here, again, sort of give you an idea of what's what. That is the telescope there. The mirror is down here. You have a whole lot of instruments strung on the bottom. That's what they call the prime focus cage up there. The secondary mirror is up there. There are tertiary mirrors as well, which I'm not going to go into. But basically, in terms of the optics, the light comes down the tube, hits the big 200-inch diameter primary mirror there, is reflected up to the secondary mirror there, or to an instrument there like a photographic plate or spectrograph or whatever. It can also be reflected back down to another, what we call the tertiary mirror, and now through the side of the tube, which it isn't possible to photograph. This thing is huge. It is almost impossible to get a photograph that really shows everything. That was the best I could do, and I only had the camera on the smartphone with me. But it is absolutely unbelievably big. You can have two guys walking side by side right up through that. It gives you an idea of the size of the South Mountain. Now, the thing that is significant about that, it was a modification by Porter of the original, what's called the yoke design. But what he did was he greatly enlarged the North Polar bearing and hollowed it out and cut an opening in it, like if you imagine a washer with a wee section cut out of it. So that is the North Polar bearing there, rotating on special pads with oil there, and the telescope can swing right down into the opening inside the North Polar bearing. So that telescope can see the whole sky above the horizon in California. So there's a little bit of the statistics. The prime focus, f3.3, so that's relatively short. It can also be used at the Cassegrain focus, which will be back down there. The Coude focus is the one where the image comes out the side of the tube. I haven't time to go into that. It was made out of Pyrex low expensive glass. The light collecting area, 20 square meters. I could quote so many statistics, but the dome alone weighs 1,000 tons. Okay, so if you want to build something bigger than that, and you're going to put it in a dome, problems start to arise, and we'll look at that later on. But it was sort of the achievement of a lifetime's ambition to go and actually see that, although it is not anymore the largest telescope in the world, but it's the largest telescope that looks something like a telescope. I'll go into that a bit later. So, just to give you an idea of the size, when they're using it at the prime focus, that is the observer sitting there in the cage, right up at the top of the tube, and he would be doing something there, spectroscopy, photography, whatever. And there are so many stories about that, like the telescope is there pointing up and the mirrors are way down below you, and there was some guy he had to try and fix something in there, and he was using a hammer, and he dropped the hammer. And it went bang, 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 bang down the tube, and it didn't hit the mirror. Fortunately, it hit the side of it. But he said his heart stopped, his light flashed before him. And I just wrecked the biggest, most important telescope mirror in the whole world. But anyway, gives you some idea of the size And if you ever get the chance, it is worth seeing. I have been around in astronomy long enough to have made a few contacts, and we got a special private tour of it, but they do public tours as well, and they're fascinating. It's now fitted with things called adaptive optics, which basically correct for any deflection. For example, the mirror. The mirror weighs, what was it, 15 tons or something, even after it was figured, and that can sag under its own weight, almost imperceptibly. But when you're doing very, very high accuracy observation and imaging, you don't even want that. So they now have a system where it will actually correct for any deformation of the shape of the mirror. Won't go into too much detail. For example, that was the telescope, although it wasn't by any means the biggest at the time. It was the first one to provide a direct image of an exoplanet. So it was groundbreaking and sky-breaking, if you like, as well. We also got a visit there to see what was also the most powerful telescope of its type in the world, the Schmidt telescope, which is basically a Schmidt camera, an astronomical camera. And what you have there is, again, a curved, concave primary mirror, and you have a correcting plate here at the front, which corrects for the aberration of that mirror being spherical. It doesn't have to be paraboloid. The correcting plate is smaller than the diameter of the main mirror, so that's called a 48-72-inch Schmidt. 72-inch the diameter of the main mirror, 48-inch diameter of the correcting plate at the front, and that's what determines the amount of light that it collects. But the advantage of that is that it gives you a very wide field of view. It has to have special curved plate that goes there, as you can see, a very strong curve. So we'll look at that, a wee bit named after O'Sheen, who provided the money, and that did the famous Palomar Sky Survey, which photographed the whole sky down to magnitude 22, which is very, very, very faint. There were 1,872 actual photo prints. If you bought the Palomar Sky Survey, you literally got a set of prints printed from the original plates, 14-inch by 14-inch. Covered 6 degrees, and you could get red and blue, or in fact it came with imaging in red and blue. The stars on the plates are actually invisible as the naked eye. They're such fine images. This was an extremely high resolution photographic plate. I got to use the one at Armagh Observatory once. I was trying to find a new faint comet, and I wanted to be able to locate it, and I got out the Sky Atlas and turned to plate 84, whatever it was, and right there's Epsilon Aurigae or whatever it was. I thought, there aren't all that many stars there. And then I saw there was a wee magnifier provided, and used the magnifier, and there were images there. You know, it was like sprinkling pepper on a white page. There were so many stars that you got lost in them, basically. So not only the original plates, but the actual photographic prints that you get if you buy this Palomar Sky Survey. The images of the painter stars are too small to be seen with the naked eye. That was the degree of fine printing that they have. So that revolutionized astronomy in that it covered huge areas of the sky. It covered everything in the sky that was visible from that area. That's also Mount Palomar. So that's down to about probably 40 degrees south of the equator, and it was so successful that they then built one in Australia, a twin one, and that then was able to cover the whole sky. So that was the first telescope that provided what we call now wide field sky surveying. And it was revolutionary, and it has never been beaten in terms of what it did in photography, but we'll come on to other aspects later on. So the 200-inch basically was the largest, and it was practical to build a single mirror. 200 inches, 5 meters. That is a huge, heavy lump of glass, and you have to try and get that up somehow, up to the top of a mountain. You know, it's a substantial fraction of the size of this room. So building anything bigger than that really wasn't practical. The Russians did do one bigger, a 6 meter in Baikonur. Not Baikonur, that's the space thing, of course. Anyway, it's in Azerbaijan. But they didn't get it right. The optics were never good enough for it to produce really good quality work. It's still there. It still has the title of the largest single mirror telescope in the world, but it wasn't nearly as good as the Palomar one. Basically, the design was not satisfactory and the manufacture wasn't up to standard. So the next step was to build what they call multiple mirror telescopes. And I again had the honour of seeing this one. The 6 individual meters of the multiple mirror telescope, and what we have over here, the large binocular telescope, is the way forward. Using computers now, you can combine the images from several telescopes together in such a way that basically they function as one telescope with the combined aperture, combined light gathering power of all the individual mirrors. And that has become the standard now for all new really big telescopes. The biggest one that you probably have heard of, and that is actually in operation at the moment, is the Very Large Telescope, very imaginative name, 4 individual 8.2 metre segmented mirror telescopes. So each of the telescopes in those domes has a mirror of 8.2 metre diameter, but it's not one big piece of glass, 8.2 metre diameter. It's a whole lot of individual segments making up 8.2 metres. That can be used as one giant telescope by what they call interferometry, and I don't have time to go into that, but again, basically using fibre optics and computers, you can combine the images from all 4 telescopes together, so if they operate as one, and you can also add in these smaller ones, which give you resolution, extra revolution in that direction, as well as in that direction there. And that is the most powerful telescope on Earth at the moment in optical wavelengths. So, Ritchie-Chrétien, I don't have time to go into the details of that, but it's basically a slight modification of the Cassegrain design. It's a catadioptric design. In other words, it uses lenses and mirrors. It's just that the design is slightly different. So they put it up on top of a very high plateau in Chile, where it has excellent observing conditions, very clear dry air, and a large number of clear nights per year, which gives what we call very good seeing. In other words, the images are not too distorted by irregularities in the atmosphere. But there are ways of getting around that, using lasers here to provide artificial stars and what we call adaptive optics. And I'll say a little bit more about that in a moment. How am I doing for time? Am I all right, Peter?
Well, I was going to say, Terry, we're kind of eating into the question time.
Okay, right. So the largest single telescope in the world at the moment is the Grand Telescope Canarias, the Grand Telescope of the Canaries on La Palma. Segmented mirror, 36 individual segments, adaptive optics for the computers, basically correct for any irregularities in the images provided by the atmosphere. Very complicated, very high technology, corrected in real time up to 700 times per second. It's on an altazimuth mount. It doesn't need to be on an equatorial mount because the computers now can correct for all that motion in the sky. But the thing about that is, as I was saying, in contrast to the Palomar telescope, it doesn't really look like a telescope. It's a big box of framework. You know, when I saw the big one in South Africa, the South African Large Telescope, which is almost as big as that, you're basically under a big engineering structure, and it doesn't look even remotely like a telescope, but it works like a telescope. So there's the individual segmented mirrors. Up there is the secondary, and then you have all sorts of ancillary equipment. Far too much for me to go into detail, but again, you will have probably 3 different focal ratios. Prime focus, a Cassegrain type focus, although Ritchie-Chrétien is basically the same thing with slight differences, and a Coude focus, which goes out through the side, and that's the longest focal length of all. I just don't have time to go into all the details. Then the next step was to go up above the atmosphere, and you've all heard of the Hubble Space Telescope and the James Webb Space Telescope. It's the latest, bigger, operating in the infrared. The Hubble, you probably are reasonably familiar with the design, solar panels just to collect sunlight to power it with electricity, and it's operates in the ultraviolet and the optical and the near infrared. Far too many discoveries to mention, but there are other ones as well which operate further into the infrared, into X-rays and gamma rays and so on, and that's the famous Hubble Deep Field, which reached out to the edge of the observable universe and found that there were galaxies. No matter how far out you looked and how far back in time you looked, there were galaxies. The current king of the telescopes in terms of what it's revealing is the James Webb. Again, I don't have time to go into all the details. It's a way out at what we call the Lagrangian point, well away from the heat from the Earth, because it operates right down into very, very cold temperatures where you're seeing into the deep infrared, and that has huge advantages. It enables you to see through dust and galaxies and so on, and to see well back in time because of it sort of counteracts the redshift. Those are basically heat shields, so that the telescope is always on the far side of those heat shields relative to the Earth and the Sun, and that keeps the heat away, and that telescope can operate down to within a few degrees of absolute zero. And it took an image of the Hubble Deep Field and sort of doubled, or 2.5 times the amount that it saw. But one of the most spectacular things is that it produced some amazing gravitational lensing images. And what we have there is a cluster of galaxies very, very, very far away, but beyond them are other galaxies. And as the light that comes from those very distant galaxies passes around this nearby cluster of galaxies, it gets bent by the gravitational field, and you get these rings, basically. So those are all distorted images of galaxies that lie beyond this distant but still closer cluster of galaxies. And that is, it's basically acts like a lens. It's called gravitational lensing, and that enables you to see even further out and further back in time. And again, that would be a topic for a talk on its own. So very briefly, we'll look at the other things. For example, radio waves, all part of the the electromagnetic spectrum. The big one at Jodrell Bank, 250-foot diameter, now I think increased to 300, is it? So anyway, 250. And the biggest one in the world is the 500-meter one in China. Now, it is fixed. You cannot make a steerable 500-meter dish. So it is basically mounted in a convenient hollow in the hills. The secondary equipment is suspended from cables from these surrounding pylons, and by moving the secondary equipment backwards and forwards, or up and down, mainly backwards and forwards, you can change where the telescope is pointing effectively. You're basically sort of tilting it. In effect, you're tilting it optically, and you can then cover quite a large area of the sky. Another thing here in Ireland, which again you may have seen if you've been to Birr, is ILOFAR, I for Ireland, and LOFAR for the low frequency array. So that's just about 200 metres, maybe 300 metres from the Leviathan. It's using a totally different sort of radio receiver. I'm not going into the details of it. A medium resolution and a medium band and a high band. And the important thing is it's part of an international network. All these telescopes at all these locations here, all built on an identical design, are connected to a central hub in the Netherlands. And that enables you to, again, operate that as an interferometer. In other words, to combine the observations from, say, Birr at one extreme and down Lassie, whatever it is, at the other end, giving you the effect of a telescope which has a diameter of that which would be 1,000, 1,500 metres or so, and there are plans to extend it even further. So Ireland is now playing a major role again in international astronomy. If you ever get a chance, ask somebody like Peter Gallagher, who was responsible for the ILOFAR development, to come and give you a talk about it. It covers a huge amount of stuff, even though it's what we call very low frequency radio waves, the opposite end of the spectrum to gamma rays and so on, but nevertheless producing absolutely amazing stuff, both on its own, it operates on its own, and also when necessary as part of that network. So we're coming towards the end now. The next step will be by far the most powerful telescope in the world, the square kilometre array. The clue is in the name. The total collecting area of all the individual dishes will be a square kilometre. Now, that's not too difficult to do because each of the dishes is identical and they're not too hard to build. But just imagine the amount of data that is collecting. That is the problem. The data streams from the new modern telescopes are at the moment greater than we can cope with, not only in terms of fibre optic to transmit them, but in terms of computing power to deal with them. But they hope that when that thing is actually built, they will have powerful enough computers to actually deal with the amount of data that it will come in. So it will produce more data than the whole of the internet as of now. So that is pretty mind-boggling. Have to mention gravitational waves very briefly. The first observations that didn't use the electromagnetic spectrum, basically Einstein's theory of gravity says that if you have two very, very massive objects moving very rapidly, or even one sort of pulsing, but in this case two moving very, very rapidly, for example, spinning around each other, they will literally distort space-time in what we call a gravitational wave. And the first ones were discovered by a pair of observatories there in Washington and Louisiana, designed specifically for that purpose. You use two of them so that the signal, if the signal isn't recorded at both observatories, then it's something else, it's something local. And there's another observatory in Italy involved as well, but that was the main pair. Far too complicated to go into detail now, but this is what they now call multi-messenger astronomy. Messenger number one, the electromagnetic waves that come from whatever object it is, from radio waves right through the gamma rays, and messenger number two, gravitational waves. Nothing to do with electromagnetics at all, but tells us an awful lot about very massive, rapidly moving objects. Again, a subject for a lecture on its own. The future, the extremely large telescope, don't blame me for these unimaginative names, 39-metre diameter mirror. Much bigger than this room, probably twice the size of this room. What is it? Certainly 1.5 times the size of this room. A single telescope with that power. It's going to need not just one set of corrective optics, but 4 sets of corrective optics, what they call multi-conjugate adaptive optics, which will operate independently but yet together. Again, I don't have time to go into it, but that will be absolutely revolutionary again. First light coming up towards the end of the decade. The Vera Rubin Observatory will be the successor to the Palomar Sky Survey, in that it will observe the whole sky down to an incredibly faint magnitude a couple of times a week. The whole sky a couple of times a week. The Palomar Sky Survey took years. So, 10 million alerts per night. And an alert is simply something that has either moved or changed brightness. 10 million every night. Talk about data stream. I haven't time to go into all the details, but basically this is going to be so revolutionary and provide so much information that it's going to be made available to any astronomer anywhere in the world, because they want everybody to be able to spot something has moved, something has changed, supernova has gone up, a near-Earth object is heading towards Earth. So there'll be no, usually much data produced by a new instrument is available only to the investigators for the first year, and then it's available to the rest of the public. Everything that this telescope produces will be available instantly over the internet to every astronomer in the world. What that is going to produce, we just cannot imagine. But some, for example, 90% of all near-Earth objects of 300 metres or larger, 10,000 Edgeworth Kuiper Belt objects out on Pluto, thousands of supernovae. Primarily what it was designed for is collecting so much data that it will tell us about dark matter, where dark matter is. Briefly, give you an idea of sizes. That outer ring will be the diameter of the extremely large telescope. That one there is Oh, sorry, that one there is the OLT, the overwhelmingly large telescope, which was never actually built. That one there is the extremely large telescope. The very large telescope, the large binocular telescope, the 30-metre telescope, which may or may not be built. Where's Hubble? Hubble is up. There's the Hooker, the Hale telescope there. Hubble is relatively small. The Giant Magellan telescope, again, they haven't got the funding for. The VLT, the 8.4 metre ones. So, to give you an idea there, that's how much bigger it's going to be. Bigger than the total light collecting area of all these other telescopes put together, apart from that one and that one, which haven't actually been built. Right, I think we'll come to the last one. The future. Who's got one of these? Right, okay. An electronic telescope, okay? It collects images, and it doesn't just sort of collect the photons on a CCD or a photographic plate. It collects them in something that you can see. There are a whole lot of new designs, basically the same design, different models available. That is the future. It's small, only about a 2-inch diameter lens, totally computer controlled, connects to your smartphone or to your laptop, and within 30 seconds, you're getting a beautiful photograph of the moon, of M31, of the Orion Nebula, or whatever. These are just the first generation. Within a couple of years, there'll be more, they'll be better, they'll be bigger, they'll be more powerful. I'm an old-fashioned astronomer. I like photons coming through an optical system directly into my eye, but I know this is the way forward. For example, that one there, you fit it in a suitcase very, very easily, and it will give you stunning astronomical photos. Not quite as good as these ones here. Congratulations to the people who have taken those ones. But for something that you can put in a small suitcase, it's literally revolutionary. So that's it. Thanks for listening. I'll try and answer your questions.
Thank you, Terry. Now, I'm afraid there won't be as much time for questions as I was hoping, but who's going to raise their hand first?
Okay, I can go home.
Just a quick one, very specific question there. You showed segmented mirrors.
Yeah.
And that's where I understand adaptive optics is.
Yeah.
Pistons
More to it than that, but part of it, yeah.
Moving them.
Yeah.
And then you mentioned the 200-inch Palomar is a single mirror.
Yeah.
What's adaptive optics?
Right. They don't bend the main mirror because it's a big, even though it's a honeycomb structure, it's just a big solid of glass. Yeah. But you can bend the secondary mirrors to correct.
So it's secondary.
Yeah. Didn't have time to go into the detail. Either the secondary mirror or the tertiary mirror can be. Basically, you have little push-pull motors that operate on the scale of a thousandth of a millimetre, that amount of fine movement, and the computer corrects all the time, pushing in out the mirror, and it corrects for any deformation in the mirror itself as the telescope moves like that, but mainly for the deformations in the atmosphere. The best example of that is if you ever look at something at the bottom of a swimming pool, whenever people are swimming around it, the image just dances around all over the place. That's what happens in our atmosphere because of irregularities in the temperature and density of the atmosphere. So the saying which the astronomers use for the terms of the steadiness of the image, it is never better than about a half arc second of arc, and that's very, very good. With adaptive optics, if we have time, I'll try and explain, but basically the computer knows what the irregularities are. It knows what a theoretically perfect image will be. It looks at the deformations in the image that comes in, and in real time it corrects them before it goes to the instrument. 1,000 times a second.
By you creating an artificial star with the laser?
Yeah. There are two ways of doing it. You can use a real star if there's one bright enough in the field of view, but most of these telescopes have very small field of views, and quite often there is not a bright enough star in the field of view of the distant galaxy that you're imaging. You create an artificial star. There's a layer in the upper atmosphere where sodium atoms can be excited by a laser shone from the ground. So you shine a very, very fine, accurate laser onto this sodium layer about 40 to 50 miles up, and it illuminates a little point of light where the sodium atoms are excited, and that's your artificial star. So you put that in the same field of view as the object that you're imaging. The telescope doesn't know that that's an artificial star rather than a real one, but the light that comes back down through the atmosphere gets the distortion, and the computer corrects for that.
Thank you.
Who's next? You all want tea, don't you?
That's it. You've got your priorities right.
Terry, there's a question that has often bothered me. In a reflecting telescope, you have a secondary mirror.
Yeah.
Right in the middle of this telescope. Yeah. Why doesn't that show up as a big black blob?
Because it's not in focus. If it's a Cassegrain telescope, a Schmidt Cassegrain, say, that you would have here, it's half a metre in front of the mirror. The mirror is focusing on infinity. Now, it does create a lack of contrast. And that's why, for example, the Ritchie-Christian model or the Maxitov is slightly better than the standard Schmidt Cassegrain because the secondary mirror is smaller. But it does reduce contrast, but it's still acceptable. Some of these photographs here were taken with Schmidt Cassegrains. They're pretty good, pretty damn good, to be honest. If you've ever seen the photographs that some of the best astrophotographers are taking of Jupiter and Saturn, where contrast is essential. Fabulous photographs, and a lot of them are taken with Schmidt Cassegrains. So there's a little bit of computer, it's not cheating, but the computer can do an awful lot in getting rid of improving contrast, for example. But yes, the secondary mirror does cause an obstruction, but I mean, if I put my thumb up in front of your spec, you can still see me, okay? Same sort of effect. You're focusing on me over here, and that is right up close in front of you. So in terms of scale, the secondary mirror is, depending on the size of the telescope, between, say, half a metre and maybe 5 metres away, whereas the telescope is focused on infinity. So it's so out of focus. It affects the whole image, but the whole image equally. It's not a little black spot in the middle.
So that's the end of the questions, I'm afraid. In 2 or 3 minutes' time, I'm going to close this meeting. You're going to come down here for tea, and then you'll be able to buttonhole Terry with the question that you didn't have the time or the courage to ask right now. But Terry, now I am going to thank you for an amazing canter through the 400-year history of the telescope, and on behalf of the Cork Astronomy Club, may I present you with this small gift of our appreciation.
Thank you very much indeed. I seem to remember that this is usually a bottle, yes, the Celeste. Very, very nice and very appropriate. Thank you very much indeed.
Right, I shall close the meeting in a couple of minutes. Just a couple of reminders.